So today I'll try to give you a sense of sort of a subfield of gravitational astronomy, which is the gravitational lensing of gravitational wave signals. I think this is going to be a very interesting tool that we will receive in the next few years. And I'll give you a brief sense of what are the challenges in, what are the prospects of detecting lensed gravitational wave signals, what are the challenges involved, and some of the means of detecting them, and also a brief summary of what such a detection or such detections would enable us to do. There is some interesting possibility of probing different aspects of fundamental physics, gravity, astrophysics, and cosmology using the observations of lensed gravitational waves. I will most of this talk will be very much within GR. So I will have maybe one slide at the very end discussing some possibility of how the lensing would look like in theories beyond GR and possible signatures of them. As most of you know, a gravitational lensing of light has emerged as a very powerful tool for astronomers, astrophysicists, and cosmologists in the sort of second half of the last century. And there are several remarkable examples of how lensing phenomena have helped us to understand different aspects of astrophysics and cosmology. For example, lensing of galaxies, both weak lensing as well as strong lensing of galaxies have provided some very strong hints of the existence of dark matter, and to map out the distribution of dark matter in the universe. There is one very iconic example that is shown in the top two panels. The top left panel shows the reconstructed image of a cluster, which is reconstructed from the weak lensing of a field of galaxies in the background. And these green contours are the reconstructed mass distribution of the cluster that is causing the lensing, which is the famous bullet cluster. And if you look at the same cluster in X-ray, which is the right plot, the top right plot, you see these density plot shows the X-ray emission from this cluster. And you can see that the emission is, the most luminous parts of the cluster are not where most of the matter is located. The matter is located in these green contours, where the density of the green contours is the largest. So it shows that this cluster has a large amount of dark matter. In fact, the mass is dominated by dark matter, which has a large offset in the luminous part of this cluster. And there are, this is only one example. And lensing has sort of served as some cosmic magnifying glasses, which enabled us to detect some extremely distant stars, for example. So again, the bottom right plot is an observation of a star, which is at gigaparsec away. I forget the exact number, but close to gigaparsecs. And this is unheard of in astronomy, right? You cannot detect stars at this kind of distances, but the star, a cluster happened to be in the line of sight between us and the star, and there is a relative motion between this distance and the star and the cluster. And astronomers were happened to be observing this patch of the sky, so a brightening up of a star at around 2016. And this, if you look at in the same patch of the sky in 2011, the star, this spot was not there. So this sort of cluster sort of acted as a cosmic magnifying glass, which sort of enabled us, possibly one of the first stars, like one of the very earliest stars in the universe. So similarly, lensing has enabled us to observe very distant galaxies and the early galaxies, etc. And another aspect of lensing is the micro lensing by much smaller objects, including stars, compact objects, and potentially other kinds of compact objects like which are broadly classified as machos. And we know that there is a possibility that a good fraction of dark matter could be in the form of compact object. And this possibility has been sort of heavily constrained by several astronomical observations. And the microlensing of stars in our own galaxy as well as the neighboring galaxies have practically enabled us to rule out the possibility of our own galaxy's dark matter being constituted by compact objects in the sort of subsolar mass range. So the here idea is that if the dark matter is comprised of a large number of compact objects, a small number of them would statistically come in between us and the starlight from our own galaxies or stars from neighboring galaxies. And this could cause a microlensing effect in the light coming from these stars. And the non-observation of such microlensing signatures have enabled astronomers to put constraints on the fraction of dark matter in the form of compact objects in the sort of subsolar mass range. And there are positive detections of gravitational microlensing, of course, and this has enabled astronomers to detect exoplanets. And here is the middle bottom plot shows a sort of a cartoon example of how astronomers are using gravitational microlensing of light to detect extrasolar planets or exoplanets. And here the idea is that if a star happened to come in between a distant star and us, this star would cause, if there's a relative motion between the lens and the source, the star and the distant star, then this would cause a time-dependent magnification, as shown in the bottom plot. And if there is a planetary system orbiting around this lensing star, then on top of this broad magnification of the star, there could be additional signatures of the microlensing by the planet itself. So that there's an example shown. There's a little additional dip that is caused by the microlensing of a planet around the system. And such microlensing signatures have been used to detect the presence of exoplanets. And so that's sort of my quick intro to the gravitational lensing. And we all know that in the last 5 years, the astronomy using gravitational observations have flowered into a full-fledged field. And that is why we are having this conference. And so far, LIGO and Virgo have detected of the order of 100 gravitational wave signals from compact binary coalescences. This includes gravitational wave signals from double black holes, double neutron stars, and mixed systems of black holes and neutron stars. And the data is public, and the independent groups have analyzed the data and have, apart from confirming the LIGO Virgo observations and discoveries, they also have detected, independently detected several extra signals, some of the sub-threshold signals as well. And these observations have resulted in an enormous amount of science. I know I'm preaching to the choir here, and most of you are very well aware of the science that came out of these observations. But still, if there are anyone who have really not followed the full science of gravitational observations, let me give you a very quick summary. Of course, these observations have provided the first detections of merging binary black holes, and they have uncovered the existence of so-called heavy stellar mass black holes, the black holes that are more massive than about 30 times the mass of the sun, which were sort of not expected based on our observations of X-ray binaries in our own galaxy, which all suggested black holes, that the stellar mass black holes would be mostly less than 15 solar mass or so. We have had some potential evidence of the intermediate mass black holes. So this particular system, GW190521, must have produced a remnant black hole that is more than about 100 solar mass. One remarkable observation of a multi-messenger observation of a binary neutron star system, GW170817, have resulted in a number of very interesting observational science from pertaining to different aspects of physics, both gravity as well as nuclear physics, but also different aspects of astrophysics. as well as cosmology. And we have had a couple of other binary neutron star candidates, which are believed to be binary neutron stars based on their measurement of their masses, and also mixer systems of neutron stars and black holes. Although we have not seen any telltale signatures of neutron stars in these gravitational waveforms, but the mass measurements from these signals are firmly in the regime of traditional neutron stars and traditional black holes. So we believe that these signals include additional binary neutron stars as well as black hole neutron star systems. There are some very strange signals, which includes this particular system, GW190814, which involves either the heaviest neutron stars that we know of, or the lightest black hole ever observed. So apart from these sort of important observational highlights, these populations of detections have enabled us to perform some very interesting tests of GR, just some of the first tests of GR in the regime of extreme gravity and extreme velocities. These have provided new avenues for mapping out the cosmic expansion history, constraining the equation of state of dense nuclear matter, and so on. And the multi-messenger follow-up from the double neutron star merger GW170817 have resulted in a whole suite of very interesting science by itself, including possible hints of the origin of heavy elements in the universe. So we know that these LIGO and Virgo detectors have not yet achieved their design sensitivities, which are expected to happen in the next few months during this upcoming 04 observing run. And there are additional upgrades planned to advanced LIGO and Virgo, including so-called A+ upgrades. And there are also possible upgrades planned to the to install new detectors in the existing facilities. These are called the Voyager idea. And there are also long-term plans for building the next generation of gravitational detectors, both in the US as well as in Europe. This includes Cosmic Explorer in the US as well as the Einstein telescope in Europe. There is, of course, in the next few years, the CAGRA has sort of already joined the observing run, and the LIGO India is also expected to join the ground-based detector network in the next 5 years or so. So it is just by extrapolating the observed rate of binaries and the expected upgrades in the detectors, we expect to detect several hundreds of detections in the next couple of years and possibly thousands of detections in the next few years. So we are really opening up a totally new branch of astronomy. And among the large number of sort of new phenomena that we are anticipating is the possible observation of the gravitational lensing of gravitational waves. Recent estimates that takes into account the observed large-scale mass distribution of the universe, such as the distribution of galaxies and clusters, as well as the observed rates of compact binary coalescence that we have observed, we expect a small fraction of the observed gravitational wave signals to be strongly lensed by intervening mass distributions, in particular galaxies. And these will create multiple images of the observed signals. And depending on the nature of the source, nature of the lens, whether these are galaxies or clusters, these multiple images, so-called multiple images, would arrive at the detector at different times, separated by time delays of minutes to weeks or even months in the case of cluster lensing. So these are analogous to the very familiar examples of strong lensing that we have seen in electromagnetic astronomy. This one particular example is a gravitationally lensed quasar. And but one remarkable thing in the case of gravitational wave signals is that since these are transient signals, their time delay can be measured extremely well with precisions of milliseconds. Although our ability to measure the angular separation is extremely poor, because as you know, the gravitational waves being very long wavelength beams, and with our network being a rather small baseline as compared to the wavelength of the waves, our ability to localize the sources is not the greatest. So it's sort of in some sense complementary to the gravitational strong lensing of light. While gravitational wave strong lensing cannot measure the image separation very accurately, what we can measure is the time delay between multiple copies of the signals that are arriving at the detector. So this sort of enables some very interesting complementary measurements that I'll sort of briefly mention as we proceed. So apart from these observation of, so when the lensing is, lenses are galaxies or clusters which have a Schwarzschild radii of 10 to the 11 kilometers or larger. When we talk about gravitational lensing of gravitational waves observable by LIGO and Virgo, their wavelengths are much small as compared to the gravitational radii of the galaxies, of the lenses. Hence, the problem can be treated in the approximation of geometric optics. So in this approximation, the lensing does not change the frequency profile of the signal. It only introduces a relative magnification. So it magnifies or demagnifies the different images differently. And it can also introduce a phase delay between the images, apart from obviously a time delay also. So essentially, these multiple copies of the signals would look the same, apart from an overall change in the magnification, as well as a potential constant phase shift between them. And in this way, it is practically impossible to identify a single strongly lensed image, although certain types of images introduce the phase delay, actually deform the shape of the gravitational signals, and our colleagues have recently shown that. Yeah.
Sorry to interrupt. There is a question on the chat box by Shayan.
Correct. Yes, the answer is yes. Yes.
Okay.
Okay, thanks. Yeah. Okay.
Yeah, but essentially the lensing phenomena is practically the same for light and gravitational waves.
Sorry, may I ask a follow-up? So here, when you are saying the gravitational lensing, so there will be you just measure the frequency difference due to the path difference of the lensed wave. That is what you can measure, right? When you talk about gravitational.
No, it does not affect the frequency profile of the signal. So what it changes at least the strong lensing, in the geometric optics, it introduces a magnification to the signal, and it also introduces a time delay, which is for different images.
Oh, I see.
So the time delay has a geometric part due to the different path, but also has a Shapiro part because of the gravitational field of the lens.
I see. So can you distinguish between these two? That the Shapiro part, combined effect you have to.
Yeah. So we can only measure the combined effect. We cannot also measure the absolute time delay. All we can measure is a relative time delay between images.
I see.
Because once you have established that these two copies of signals are coming from are coming due to these are the lens copies of the same original gravitational wave signal, we can measure the time delay between them, which contains some imprints of the lens mass, geometry, etc.
I see. Thanks.
Yeah. So I started saying that it is practically impossible to identify whether the single signal is lensed or not. There is some caveat. I'll mention this after 2 minutes. But so The reason is that if even if the strong lensing introduces multiple images, some of these images could be sub-threshold. They could be so dim that they cannot be detected with a certain signal-to-noise ratio threshold, which means that we will only detect the loudest among the lens signals. And it is practically impossible to tell whether that signal is magnified if it's or not, because a distance signal that is magnified would practically look the same as a close by gravitational signal. So essentially, they would appear as a compact binary coalescence happening at whatever closer in our close by universe. However, there are ways of distinguishing it, and this is due to the fact that the additional phase shift caused by the lensing would affect different modes of the gravitational radiation differently, and it can actually introduce a shape change in the gravitational wave signal for certain types of images, so-called type 2 images, which is in principle distinguishable. So if you leave that minor detail, I think it's sort of safe to assume that one cannot actually identify whether a single gravitational signal is lensed or not. So this can cause some interesting effects if you do not, and it can even cause some observational biases if you do not take care of this properly. I will come to that. But this is sort of analogous to this gravitationally lensed star that I talked about in my first slide. This is this first image that I showed in the very first slide. It's an example of a gravitationally lensed star that is at a distance of about 9 billion light years, about 3 billion parsecs away. Sorry, 3 billion parsecs away, which was found because of the gravitational lensing. And similar to this is a very rare phenomenon. And similar to this, a small fraction of the very distant binaries could be highly magnified due to the intervening matter between this. And this, for example, would enable us to detect some very, very distant binaries, potentially the first binaries formed in the universe. Although our detectors have a much smaller sensitivity horizon. So this is a plot from Dai et al., which sort of investigates how how lensing could sort of significantly enhance the horizon of detecting some of the binaries. And you can see that this is, for example, this green curve here shows the traditional horizon distance of a certain detector in this advanced LIGO as a function of the total mass of the binary, and it sort of it can reach to cosmological relationship of the order of 2. However, due to lensing, it also is able to detect some additional sources which are at much larger distances. This is a rare phenomenon, but it really enables us to detect some of the much larger distance because of this cosmic magnifying glasses. And these and because of this lensing magnification, it can actually introduce some bias in the parameters that we extract by from the observed signals. The reason is that the distance, the luminosity distance, is completely degenerate with the lensing magnification. So this is what I said. Like a nearby source would be practically same as a distant source that is highly magnified. And because our distance estimation is biased, as most of you know, we have no way of directly measuring the cosmological redshift from gravitational wave observations, because the cosmological redshift is totally degenerate with the mass scale of the binary. So if a binary is redshifted because of the cosmological redshift, essentially by comparing data with theoretical models that does not include this cosmological redshift, essentially we would infer it to be a higher mass binary, because higher masses would involve lower frequencies. So, and the lensing magnification and the way we correct for this cosmological redshift, or by the way we extract the real source frame mass, is by assuming a cosmology. So we extract the luminosity distance from the data, which we can do. And by assuming a cosmology, we can calculate the corresponding cosmological redshift. And then we can correct observed the mass, the so-called detector frame mass, and we can extract the source frame mass distribution. So the source frame mass of an individual signal. And because of the lensing magnification, our observed distance will be biased. Instead of the DL, it's the true luminosity distance. What we'll be measuring is a DL by square root of mu, where mu is the lensing magnification. And we will be extracting a biased value for the luminosity distance. And when we compute the corresponding cosmological redshift, we will get a bias estimate of the cosmological redshift. And we use this bias estimate of the cosmological distance to correct for the mass scale of the system, and we will estimate a biased estimate of the mass. So we will estimate, we will incorrectly attribute a higher mass to the compact binary system that we are measuring. And in fact, some astronomers have claimed that the heavy mass, all the heavy mass black holes that LIGO have observed are in fact due to lensing, due to gravitational lensing. However, most of the astrophysicists and astronomers disagree with this statement because it requires a much more fine-tuning of the not only the either the lensing distribution, or one has to assume some very non-trivial models of the merger distribution of compact binaries. And one can actually explain the observed mass distributions without invoking. So it's to make a statement that most of the LIGO's massive black holes are dense is a very strong statement, and we don't have that level of extraordinary evidence to make such a claim. And here is sort of one study that looks at this. So here is it's a forward modeling of how what fraction of the binaries will be lensed if you assume some fairly standard models of the mass and redshift distribution of compact binary mergers and the mass distribution of galaxies in the universe. And we ask, as a function of the redshift mass and the observed redshift, what fraction of the observed binaries are likely to be lensed. And that is shown by these density plots. And so, for example, these redder and bluer regions shows very small value for the a priori lensing probability. And here on top of this shows the posteriors of the binary black hole events detected by LIGO and Virgo during the first and second observing run. So most of these events lie all of the events lie in the region of very small a priori lensing probability. So without invoking some very non-standard models of the binary properties, one cannot explain this using lensing. And there is newer observation, there are newer analysis using the entire O1, O3, sorry, O2 and O3A data, which is put forward by LIGO collaboration, which sort of reconfirm this. But indeed, we do not know the actual distribution of the properties of the merger. So in principle, one can have this situation, although it is pretty non-standard, I would say. So one sort of telltale signature of lensing is the production of multiple images. So in that sense, that is the real smoking gun evidence of lensing, whether this sort of claim is true or not. So in that sense, that there is a lot of effort going into identifying such strongly lensed signals, and again, it is this effort is complicated by the fact that most of our events, if not all, have very modest signal to noise ratios. It's very small as compared to the signal to noise ratio of electromagnetic observations. Right. So it is not very easy to identify a handful of potentially strongly lensed signals among hundreds of unrelated gravitational signals. So our clue would be to look for signals that are similar in shape, because we know that geometric optics will not deform these signals. So what we are looking for is signals that are similar in shape, coming from the same region in the sky with time delays consistent with the lensing population. And this is challenging because of the low signal-to-noise ratios. So, and it is checking the consistency of the two observed signals directly may not be ideal, because the lensing, since the two images would involve two different linear combinations of polarizations. So if I take a step back, you know that according to GR, gravitational waves have two polarization modes, and a given detector would observe a linear combination of the two polarization modes. And because of the time delay between multiple images, it could be hours or weeks in the case of galaxy lensing, the Earth would have rotated in between them, and these two images would involve, in general, two different linear combinations of the same polarization. So they may not look exactly the same. So one has to resort to some higher level of inference. So we had developed a Bayesian model selection method to identify strongly lensed events in LIGO Virgo data. So what we do is, given the two observations, which have two data sets, D1 and D2, to observe gravitational signals, we can compute the likelihood ratio, or the posterior probability ratios of posterior probabilities of two different hypotheses. One is that these two signals are produced by the strong lensing of the same merger signal. And the second hypothesis is that these are produced by two different mergers. And one can write down this Bayesian likelihood ratio, or Bayesian odds ratio. And if you simplify it, it comes with a very simple and remarkably simple equation. It basically turns out that it is equal to the inner product of the posterior distributions of the binary parameters, such as its redshifted masses, sky location, spins, etc., which is inversely weighted by the prior distribution of these parameters. So it's intuitively true why this has to be intuitively obvious why this has to be true, because, for example, the lensing, if two signals are lensed, then they have to come from the same locations of the sky. This means that the posterior distributions of the sky location should overlap highly. Similarly, if these two signals have coming from the same merger, their signals should look the same. The frequency evolution has to be the same. This means that the redshifted masses that we estimate from the two events should agree very well. So here is an example from two simulated observations. So here is, for example, the reconstructed posterior distributions of the primary mass and the secondary mass from the two simulated events, while the star is the actual distribution. These two contours are the 90% credible regions of the estimated posterior distribution of the masses. And in general, because the lensing magnification is different for the two images, they can have different precision, or the posteriors can have different widths or different areas. That's why they don't look the same, but they should overlap. And the second bottom line shows their reconstructed source location, which also overlaps nicely. So apart from this consistency of the observed parameters, one can also make use of the understanding of the distribution of time delay that our non-lens distributions would produce. For example, this can be done by some forward modeling, because we know that the major distribution of large-scale structure in the universe. So from the galactic surveys, as well as the modeling of dark matter halos, etc., we can predict the mass distribution of galaxies and clusters. And we can do a forward modeling of generating compact binary objects in the universe, and computing the lensing magnification and time delay. and calculate the expected distribution of the time delay between detectable lens signals. And so here is, it of course depends a lot on the assumed properties of the mergers and so on, but they broadly follow similar shapes. So here is, for example, this red shape shows the distribution of the logarithm of the time delay in hours between the two magnified images of lensed images, according to certain assumed properties of the black holes, binary black holes. And if we vary this, you get some slightly different distribution, but broadly they're consistent. And in contrast, the distribution of the time delay between unrelated merger events is assuming these as Poisson processes, we can calculate the distribution, and they look very different. And one could use this also to identify lensed events. For example, at this current particular sensitivity of advanced LIGO, if we observe signals with very small time delays, then it prefers the lensing hypothesis, although it does not confirm it. So by combining these sort of two different ways of identifying or calculating the likelihoods of the lensing versus unlensing hypothesis, one can improve our ability to distinguish between lensed events and unlensed events. And this is a result from a simulation. So this horizontal axis is a likelihood ratio based on the consistency of the shape of the signals, as well as the location of the signals in the sky, etc. And the vertical axis is the likelihood ratio based on the distribution of time delay between multiple images. And in the case of unlensed, is from a large simulation set, and the sort of CN dot shows how these unlensed signals would distribute in this sort of parameter space. And on the other hand, the lens signals would typically show large values of these both time delays. So this means that if a signal has very large likelihood ratio for both these base factors or likelihood ratios, then the lensing hypothesis is highly preferred. On the other hand, if signal lies somewhere here, the unlensed hypothesis is preferred. Now we have performed searches for identifying signatures of strong lensing among the LIGO Virgo binary black hole events. This is the result from the first two observing runs, the same sort of likelihood ratios based on the consistency of shape and the time delay distribution. And we only show here the pairs of events that shows the highest value of the likelihood ratio. So this means that this is, of course, the event pair. These are the GW17 0.14 means the GW signal observed on 2017 January 4th and the 2017 August 14. This is the pair that shows the highest evidence of lensing, but even that is less than, much less than 2 sigma. So there is no very strong evidence suggesting that this pair is lensed. And in fact, this was followed up by the IAS group a couple of years ago, later than this. And their analysis also included some of the additional effects, which is the so-called Morse phase, which I mentioned earlier, briefly alluded earlier, that the lensing can also introduce some additional phase shifts between the signals. This is a constant phase shift, pi by 2 or pi or 0. And when they reanalyzed the data, including these additional effects, they also identified this pair as the most likely candidate. And they also performed a sub-threshold search to identify whether there are any sub-threshold signals that are consistent with this event pair. And they did, in fact, identified a enigmatic sub-threshold signal, which was consistent with the parameters of this pair. And more interestingly, they also found that the phase delay between this multiple images is consistent with what is expected from this, called Morse phase, a phase difference of about pi. And they also looked at this patch of the sky to identify, but of course, the time delay between the signals was much larger than what we expect from galaxy. So if this is indeed lens, then the lens has to be a cluster-sized object. And they looked at the patch of the sky produced by the joint posterior of the sky location posterior from these images, and looked at the clusters, the known clusters identified by Planck. And there are a few clusters that are lie in these broad contours of the localization that they identified. However, to explain the observed magnification ratio and the time delay, one has to observe some very peculiar lens configuration, which makes the authors themselves conclude that the lensing interpretation is actually has to be rather doubtful. So one has to invoke some very peculiar configurations. So that was some excitement, and the analysis was repeated using data from the first half of the third observing run also. Again, there were no candidates found with some real significance, again, less than sigma or so. So far we have not found any evidence of multiple images. However, so why do we care? So I will speed up because I'm running out of my time. So there are some very interesting signs that one could do if you identify lensed, strongly lensed continuous sort of gravitational signals. One is that by combining this from electromagnetic observations, there is a possibility of localizing a binary black hole signal in the galaxy, or identify the host galaxy of the binary black hole signal, and potentially even localizing it at sub-galactic scale. And this is extremely important and impossible otherwise, because as we know, our ability to localize sources in the sky is actually rather poor. And localizing a binary black hole to its host galaxy can potentially provide a lot of information about the formation channels of such objects. So it's, in some sense, that's a very interesting science that one can do. Another idea is that observing multiple images due to strong lensing is like having multiple detectors to observe the same signal. So the idea here is that because there is a time delay of hours to days or even months between multiple images, the Earth would have rotated in between. And these multiple images would involve different linear combinations of the same polarization. And it is practically equivalent to doubling or multiplying the number of gravitational detectors in the network. So it's a cheap way of increasing, doubling the size of your network. And this would allow us to extract the polarization content of the signals much more accurately, which is pretty hard to do otherwise, because we know currently, for example, we have 3 detectors and 2 LIGO detectors are nearly parallel. So, in practice, we have only sort of we measure 2 different linear combinations of the same polarizations. And if you want to now test whether this polarization content is consistent with the GR prediction, one has to check whether one has to rule out the presence of additional polarization modes. And there are ways of doing it. But it would involve measurement of multiple linear combinations of these polarizations. And even with Kagra and LIGO India, one will have essentially 4 different linear combinations. And in general, theories of metric theories of gravity can account for up to 6 polarization modes. And however, if you observe a lensed gravitational signal using these 4 detector network or a 5 detector network, basically you have a double number of linear combinations to work with. And so one of our young colleagues, Srishti, investigated this, and she found that our ability to distinguish between different models of the polarization content would significantly improve when we work with lensed gravitational signals. So far I was talking about lensing in the geometric optics regime, which is typically the lensing regime that we all see in the lensing of light. However, in the case of gravitational waves, we have a possibility of observing the wave optic of NFX. that's just interference and diffraction of the lensed gravitational waves. And this happens when the Schwarzschild radius of the gravitational lens is comparable to the wavelength of the gravitational waves. And this can happen when the lensing object has a mass of tens of solar mass to up to tens of thousands of solar mass. And this will introduce very characteristic deformations in the observed gravitational signals. And in the case of a point mass lens, this can be exactly calculated and very easily calculated. And this shows, for example, how this micro lensing would deform the gravitational signal. So here, for example, this gray trace shows the unlensed gravitational signal, while these red and black shows the deformations introduced by a gravitational lens of 100 solar mass and 1,000 solar mass, etc. So one can actually calculate the expected deformation, and we can parameterize them in terms of two extra parameters. One is the mass of the lens, as well as the impact parameter of the ray. And we can similarly compute we can introduce a likelihood ratio or an evidence ratio or a Bayes factor between sort of two hypotheses. Given an observation, we could ask whether this signal contains deformations due to microlensing or not. And we can perform searches to look for evidence of such microlensing effects. And this has been done in the data from 01, 03, 01, 02, 03A, as well as the additional events discovered by the IAS group. And this is, for example, the distribution of the Bayes factors that support the microlensing hypothesis in each gravitational signal. And you can see that the largest Bayes factor is of the order of E. It's the log Bayes factor. So there is no significant evidence supporting that we have observed signatures of microlensing in the gravitational signals. And this non-detection can actually be used to put a constraint to bound the abundance of high mass compact object that could be forming dark matter. And here his idea is that if the dark matter is comprised of compact objects in the mass range of about 10 solar mass to 10,000 solar mass, or 100,000 solar mass, then these compact objects would introduce microlensing effects in the gravitational signal that we have observed. At least a fraction of them should show these microlensing effects. And the fact that we have no evidence of such microlensing can be used to put an upper limit on the fraction of compact objects in the form of, fraction of dark matter in the form of compact objects in the mass range of about 100 solar mass to 10⁵. So we have recently put a bound saying that only up to at max about 80% of the dark matter could be in the form of compact objects in the mass range, in this mass range. It's a very weak bound. It's practically has no scientific value yet, but this is the first result using this gravitational lensing of gravitational waves. However, in the next few years, we'll be observing hundreds to thousands of gravitational signals. And if we continue to observe no such lensing signatures, microlensing signatures, these bounds would significantly improve. And so it's a new way of probing the nature of dark matter, just like the microlensing of stars have helped us to constrain these compact dark matter in a different mass range. So far, I've been entirely sort of discussing lensing in the in GR. It's a fairly nascent field, and recently people have started looking at the effect of lensing of gravitational waves in alternative theories also. So in general, they have discovered that in theories beyond GR, at least in certain theories of gravity beyond GR, new degrees of freedom will be introduced, and which can introduce potentially new observable effects. So for example, even with a single image, the different propagation eigenstates, similar to polarizations, would introduce the birefringence phenomena. And depending on the time delay introduced by the lensing mass distribution, this can introduce, for example, scrambling of these signals. For example, the time delay is small, it would cause something like this wave optics effect that I've shown, right? You have multiple propagation modes traveling at different speeds, and they would interfere at the end of the lensing, and basically scramble the signal. And if the time delay is longer than the duration of the signal, then basically they would introduce something like echoes. So you would see multiple copies with a time delay, and so on. And these are all even within a single image itself. So it is similar to sort of the standard lensing producing multiple images. So there are very interesting potential observable effects, and people are just starting to calculate these effects. And I hope that lensing can also be a very interesting way of testing GR in the future. So let me summarize. To give you a big picture, we know that the gravitational lensing was sort of the first observation of Eddington was a means of testing Einstein's theory, but eventually it became a powerful probe of astrophysics and cosmology. And it's a similar story for gravitational waves, and now it has become a very unique branch of astronomy. And we expect that the first observation of the lensing of gravitational waves in the next few years, and it is very likely to become a very powerful tool for physicists, astronomers, and cosmologists. So let me stop here, and thank you very much.